Well, good morning, everybody. My name is Porquet, and in this talk, I would like to share with you my experience, actually my very first experience of doing Linux development, which was at the time porting Linux to a new processor architecture. So the story is that 3 years ago now, I was hired by the LIP6, the computer lab in Paris, part of the Sorbonne University, and more specifically their system on chip department, to port Linux to the new processor architecture that they were designing at the time, or that they had actually almost finished designing, called SAR. So in 2 words, it started like about almost 10 years ago now, in 2007, with this first national project called SOCLib, whose goal was to build a library of simulation models in System C in order to prototype system on chip. And a couple of years later, they came up with SAR. So it's 2 consecutive European projects whose goal was to define a massively parallel and scalable processor architecture. So think like thousands of processing cores around a network on chip, with the kind of really nice feature of having fully shared and hardware maintained coherent memory. So for this presentation, we're going to try to follow the incremental procedure for porting Linux, like first to a simple monoprocessor system. So 1 single CPU, 1 memory bank, and just like the minimal amount of peripheral devices that we need. To a multiprocessor system, so basically almost the same, except that we have more CPUs now and a slightly more complex interrupt controller. And finally, the full architecture, which is multi-node NUMA system. So the first question, one asks when porting Linux is, what is a new port? And as someone 2 years ago at this very conference said, Marta Rybczynska, and it was later reported by LWN.net, you have like 3 meanings to the word porting. And in my case, I have to say, it took me a couple of weeks to be able to answer this question, because as you may have seen in the pictures before, SAR is equipped with MIPS32 compatible processor cores. So basically, it means that my port could have easily fallen into the second category, except that in SAR, the virtual memory model was radically different from those of the MIPS family, and I would have had to drastically change the MIPS branch in order just to introduce my port. And actually, someone in the project had tried to do that a few years before I started this job, and had failed. So I was like, OK, let's not do that. And I came up to the conclusion that the most logical and interesting choice was to just start a new port from scratch. So that's what I did. So how to start porting Linux from scratch on a new processor? Well, it's really a 2-step process at first, at least to get an initial port working. First of all, Linux needs a minimal set of files that define a minimal set of symbols just to be able to compile. And then once we have that, we can notice that the boot is extremely sequential. So we can basically leave a lot of functions empty at first and implement them gradually as we go, which really helps writing all the code that we need. So here we have the typical layout of an Arch port. So in configs, we have the default configurations for the supported systems. In drivers, I had all the SAR-related drivers. So usually you don't have drivers directly in the Arch directory. You want to put them in the top level drivers directory. But in my case, I wanted to be like really self-contained, so I just put everything in the same directory. Then in include, you have all the Arch-specific headers. So I'll get back to that in a moment. Then in kernel, you have all the kernel management stuff. In lib, you have some utility routines, often written in assembly language to be more efficient. So everything like memset, memcopy, and so on. And finally, in you have all the memory management stuff. And what's interesting to see at this point is that only with this layout, if you try to already compile, like you don't have some weird error, like doesn't tell you anything, like already just points you like, okay, what is the first thing you should implement? And in that case, it's like, okay, I can't find a makefile, like please implement some build system. So basically that's what you do, like you start by completing the build system. And in that case, it's basically defining a default configuration for the first system you want to support. You want to have a first kconfig and a makefile. And from then, you can basically like start initializing the first configuration and even like customize it and even run make. Obviously, it's not going to go very far because you don't have any code, but you can do it. So next is the code. So this minimal set of files, which define this minimal set of symbols, well, the matter in the order in which you implement all of that doesn't really matter, but at some point you're going to have to look at the headers. So the headers, they are split into two categories. You have ASM, which contains the Arch-specific headers that are usually more like internal, for internal use only. And then you have the UAPI headers, which are meant to be exported to user space. The interesting about headers is that they represent a really big portion of a port. Like in my case, it was about 30% of all the codes are in the headers. And I checked with other architectures, like the newly reintroduced H8300, and it's about the same. It's about like 30%. Interestingly enough, it could actually be much higher than that. But thanks to the ASM generic layer, it's I wanted to thank you afterwards, but yeah, well, thanks to this guy, the job of porting all of the headers is made much easier because basically for every header that you don't have to customize for your own architecture, you can use a generic one, which usually does the job pretty well. So yeah. So once you have your minimal set of files and you're like sort of able to start compiling, then you have to start implementing the functions. And identifying the boot sequence is really useful in that case. So obviously it's much bigger than that, but here I really wanted to highlight the Arch-specific functions that you have to implement in order so you can progress to having a functional init process, which is basically your goal. When you port Linux, like the ultimate goal is to have init running and you want a prompt. So for that, we have like 6 really important functions that I'm going to try to explain. Starting with kernel entry, the early assembly boot code. Oula. So this early assembly boot code is usually like really scary at first because it's written in assembly code and it does stuff like you don't really understand. But in the end, when you really look at it, it's not that complicated. It only has to perform very few tasks in order to like sort of bootstrap the system to run the first Arch independent C function, which is start kernel that Linux provides. So the very first step is to reset the system to a known state. Because at this point, we don't know what happened before. Like, we don't know if it's the first boot or if we just reboot it. We don't necessarily know which bootloader was used to load us in the first place. So basically, just out of safety, we reset the processor to a known state. We clear the memory, the BSS segment, so we know that we're good. Then often we save the bootloader arguments, so what the bootloader gave us, which is often a device tree description. And finally, not finally, but we arrive quite soon to like the main task that this early boot code has to do, which is initializing the page table for us to enable the virtual memory and jump into virtual space. And so for that, we have to map the kernel that is in the physical memory. We have to map it at the typical 3G offset in the virtual address space. And well, the trick here is that this mapping must be done twice. Because we have the first mapping, the usual one, and we also have to initialize an identity mapping. Why? Because we can see on this snippet of code, like between the moment we enable the virtual memory and the moment we actually jump, we change the program counter to actually jump into this virtual address space. We have a couple instructions that are kind of in between. And without this identity mapping, it wouldn't work. So it's really just for those two instructions that we need this second mapping. So we enable the virtual memory, we jump into the virtual address space, and then we're good to go. The only thing we have to do is to set up a stack register so we can like do stuff on the stack and call functions. And we can finally jump to the start kernel function, which Linux provides. The start kernel function really soon will call one of the first Arch specific function that we have to provide, which is setup Arch. So setup Arch varies a lot in terms of complexity when you look at many different Arch ports. But in the end, it pretty much does always the same thing, which concerns memory. So basically, at this point, what we want to do is discover the physical memory that's available for us in the platform, usually by scanning the device tree and looking for the different physical memory banks. And we want to register them into the mem_block layer. Once we've done that, we can finish configuring the mem_block layer and finally map the physical memory into our physical address space so we can have access to all of that memory. So that's basically what setup Arch does. And once setup Arch is finished, we're finally able to allocate memory, which was not the case before. A little after that, we have trap init. So trap init deals with the whole interrupt and exception infrastructure, for which trap init is really the tip of the iceberg because this infrastructure is kind of complex. And one thing that's interesting at this point is that before trap init, if ever something happens, if ever we have an interrupt or an exception happening, everything crashes, like because we don't have like anything to catch that. So what trap init actually does is that it installs this exception vector. So the exception vector are those few lines of assembly code that will receive the exception, find the cause, why are we here, and find the subhandler that can deal with this cause in the most appropriate way. So basically, trap init configures the processor to use this exception vector and initialize the array of function pointers to fill it with the right functions, the right subhandlers. So just an example of subhandlers, they're usually not very complex. They're like a few lines, or actually more because those are macros, but they're not very complex in the sense that they do pretty much the same thing. And they also like quickly jump to some C functions which take care of the more complex processing of the exceptions and interruptions. So a little after that, we have mem init. So in the overview, we've seen the item number 1, number 2, number 3, and now we're like at number 4, where we can release the free memory, so everything that memalloc has not reserved or allocated, which is really most of the memory. Most of the memory is free at this point. And this free memory is released from the memblock layer and pushed into the body allocator, which is the page allocator. And this happens right before we are able to kickstart the slab allocator, so kmalloc, and the vmalloc infrastructure. And from then, I think the memory is pretty much like all initialized and can be fully used. The last two functions are init IQ and time init that I will talk a little after that. So init IQ, we want to initialize the first interrupt controller. So basically what happens, at least in my case, is that I will scan the device tree looking for nodes that are identified as interrupt controllers. I'm going to find them. I'm going to find the associated driver, and I'm going to like bind them together. In case you're using an interrupt controller that already has support, you don't really have anything to do more than that. In the opposite case, well, then you have to write your first device driver. Yay. So in my case, the interrupt controller was really simple, and the driver is extremely simple as well. All it has to provide is a few functions like mask, like in order to mask interrupts or to unmask interrupts, and we have to provide a interrupt handler. And to give you a rough idea, in my case, it was about 70 lines of code, so it's very, very simple. And finally, to conclude this kind of first phase of the boot, we have time init. So time init will finish initializing the timekeeping infrastructure. And for that, Linux needs two types of abstractions, or two providers. Linux needs a clock provider and a clock source provider. The clock provider will give us like a frequency. In my case, I only had a simulation of the infrastructure, so I didn't have a proper clock provider, so I cheated a little bit, and I put directly a frequency in the device tree, which was enough. For the clock source provider, it's again like subdivided into two abstractions. So we need what is called a clock source device, which basically has to give us a monotonic timeline. So think of it as just counting system cycles, 1, 2, 3, 4, 5. And on this timeline, we have a clock. We need a clock event device which is able to raise interrupts on this timeline. So basically, we want to be able to count periods of time. And so that will be our second device driver. What's interesting is that once we have that, Linux is able to do something that is called like calibrating the delay, which is counting the number of loops we're able to perform between two, like in a jiffy. And what's cool is that if Linux is able to do that, it kind of validates everything that I've presented you so far, because calibrating the delay, uses everything we've seen. So after this first phase of the boot, the road to having a functional init is still like long and difficult. But well, we're just going to see like a few, the few main difficulties on this road, starting with the process management. So in Linux, the process management is mostly Arch independent, which is really nice. The only two things that we have to provide as Arch-specific infrastructure is setting up the stack for new threads and switching between two threads. So setting up the stack for new threads comes from the fact that Linux is extremely lazy, as you might already know, and Linux only know how to resume threads. So when we create a new thread, instead of saying, hey, Linux, here is a new thread, we say, hey, Linux, here is a new thread for which we invented a past, and all you have to do is resume it. So we have to basically manipulate the stack of this new thread to like invent a new past so that when Linux resumes it, it can return to something that we invented and that can like bring us to the thread to actually execute useful code. Yeah, and then we have like 4 more aspects to deal with. Well, first of all, when Linux will try to execute this init, this first user space application, even before the processor will execute the very first instruction of this application, it's going to crash. That's normal. It's because, once again, Linux is extremely lazy and will not map anything in the page table before being asked to. So this means that we need a page fault handler so we can catch memory faults. And so for that, we have to enhance the interrupt and exception handler with the ability to process page faults. Now we're able to like execute a few instructions in our user space application. But if we want to do something better than just like an infinite loop, we want this application to be able to ask some services to the kernel. So we need to complete the system call infrastructure. So we need to define like the list of system calls that we'd like to support. And we have to enhance the interrupt and exception handler so we can receive syscalls and process them in the right way. And after that, we can basically have our own Hello World user space application where we're able to open the console, for example, and write something to it. So usually after Hello World, you take some vacation, you're super happy, and then you come back and you're like, okay, I want something better. Like I want to have a real init that's able to like actually do what init is supposed to do, which is start child processes. And for that, you need to complete the signal management infrastructure so that init can run child processes and communicate with them. And for that, there are like a few Arch-specific pieces of code to add to the port, which mostly deal with the fact that when an application receives a signal, we have to make it so that we want to alter the code, the execution, the flow of execution of this application so that it will execute the signal handler. And finally, the last thing that we want is that the kernel often needs to exchange data with user space applications. And well, accessing user space data is kind of dangerous because you don't know if it's mapped, like it might crash. So you want to protect those access. And so you need to like come up with some sort of infrastructure that makes it so that the kernel, when it accesses user space data, and if ever it crashes, it's not going to crash the entire system, and we have a way to like detect that something went wrong and that we can like catch the error and fix it in the proper way. And finally, about 5,000 lines of code later, and definitely not this amount of money. Remember, I was working in academics. Well, you have an initial port on a monoprocessor system. So that's basically, in order to like illustrate that, I ported micro-clipc as well as crosstool-ng and buildroot, so I was able to have a little system that on which I could run a few commands. And then I switched to implementing support for multiprocessor systems, so SMP. So the very first step for implementing SMP once again has to do with headers. Those again, so basically you have to like go through the list of all the headers once more in order to identify those for which you had used the generic version, except that for SMP it's not possible anymore. You have to customize them for your own architecture. And all of that usually has to do with atomic operations. Because for atomic operations on a monoprocessor system, usually it's very easy. You just disable the interrupts, you do what you have to do, and you re-enable them afterwards. And everything went fine, you are atomic. On SMP, it's more difficult than that because you have multiple processors working at the same time and probably maybe accessing the same data at the same time. So usually what you have to do is to use some special CPU instructions to deal with that. In my case, it was the typical pair of instructions, link, load, store, conditional, that are used on many RISC architectures, so that atomic operations are actually atomic. And so you have basically a bunch of headers to re-implement. The second big step in implementing SMP support has to do with EP, so inter-processor interrupts. Well, what are EPs? So EPs are like one processor wanting to send an interrupt to another processor. There can be various reasons for that. The most typical are that one processor would want to wake a processor that was asleep and tell it like, hey, there's some work to be done, like, can you do it? Or it could be for executing a special function, or actually to put a processor to sleep. So this EP infrastructure, which is like mostly software, also has to rely on the hardware interrupt network. And so for that, I gave up on the small ICU that I presented you and the small timer controller, and I used another component that was more powerful and that could basically offer internal timers as well as mailboxes for EPs and migration of IRQs. And lastly, we have to deal with the boot, because when you boot one CPU, it's one thing. When you have to boot multiple CPUs, well, the process is a bit different. So here I'm showing you the boot sequence from the boot CPU's point of view, like the main CPU's point of view. So I won't go in too much detail, but basically what happens at this point is that we have three things to do. First, we have to discover the secondary CPUs that we have in our system. And we usually do that by just scanning the device tree and identifying the number of secondary CPUs that we have. Then we have to build this spatial page table that is called ID map for the very good reason that for secondary CPUs, they're going to have the exact same issue that the first CPU, which is that when they boot and when they enable their MMU, the virtual memory, there will be also like this very little gap between having the virtual memory enabled and the fact that the program counter like switched to the virtual address space. And so we have to have this spatial page table with an identity mapping. That's why it's called ID map that will make them boot properly. And finally, the last key point is the boot of the secondary CPU itself. For that, we usually have two choices. The first one being not very efficient, but very simple. So the first one, the speed knock boot, is basically the bootloader will just start every CPU and send them to Linux. So all of them will like start executing the same assembly code at the same time, or almost. And only one of them, usually based on its hardware identifier, will say, okay, I'm the boot CPU. I'm going to take care of like all the first initialization. And all the other ones are going to say, okay, I'm not the boot CPU. I'm going to wait on this spin lock until I'm like being told that I can exit this loop. Except that in that case, you have like basically everybody running at the same time, which is awful for power consumption and other things. So quickly enough, you want to have a better boot procedure than that. And so usually you go for the EP boot. So in the EP boot, you need some support from the bootloader so that the bootloader puts all the secondary CPUs to sleep with their IRQ enabled so that the boot CPU, when it has to wake those secondary CPUs, it just has to send them EPs like one by one to bring them up. And so a bit after like 35% of increase in the code base, well, yeah, you're able to run a multiprocessor systems with a few processors. So now let's talk about the real architecture, this SAR architecture that I was telling you about at the beginning, and which was the goal of my job, basically. So this multi-node architecture is basically a multi-processor system, just like the one we've just seen, but multiplied into several nodes. And theoretically up to 256 of them. So those nodes are architectured in a two-mesh network on chip. What else can I tell you? We have this I/O node at the top right, which contains peripheral devices. So usually that's off chip. Everything else is on chip. Well, I don't know if I have enough time. Yeah, I guess I have enough time to digress a little bit. The L3 caches are actually like one layer up. That was another part of this academic project. This was to show some new manufacturing technology, including like 3D stacking. So the whole like L3 layer is one stack, one layer above. And well, obviously the external RAM is still like off chip. Yeah, so basically we have the same system as before, except that they are like in different nodes, and we have a lot of those nodes. What's very interesting in this architecture for us as kernel developer is the memory organization. And the memory organization of this chip is kind of special in the sense that the physical address space is shared. Like every processor has access to the whole physical address space. but this physical address space is physically distributed in each of those nodes. And that you can see by the address format. So the address is on 40 bits. The 32 lower bits are addresses that are local to a node, and the 8 first bits tell you the coordinates of like where this address brings you to. And so in the end, if you look at the full address space, you will basically have segments of memory, like little segments of memory, usually like 64 to like 128 megabytes every 4 gigabytes. So it's extremely sparse, which makes our job very difficult. So basically the main question the main issue I had to address was how to map this memory in Linux, in the kernel. The first approach, which was very simple and worked, was to actually kind of ignore the NUMA aspect and this multi-node aspect, and to only map the physical memory that was in the node 0, and everything else, all the other memory, I would consider as high memory, and we would only access that through the K-map infrastructure. So before I come back to this memory mapping problem, let me just tell you quickly about the interrupt network, because it's also like the second sort of aspect that was very different from just the multi-processor system. In this case, basically, we have one interrupt controller per node. And in the node I/O, we have this other component that we called I/O peak, which basically concentrate all the interrupts from the peripheral device that are in the I/O cluster, in the I/O node. And instead of having the I/O peak, having a lot of interrupt lines that are very difficult to route to when you manufacture the chip, instead it will send network packets to the node local interrupt controllers. So, well, I won't go into detail into the software implementation, but to give you a rough idea, from basically like from the monoprocessor support, if I counted just the interrupt controller and time controller, we had about like 200 lines of code. And then for multiprocessor and multi-node, each time we added 300 lines of code. So at the end, yeah, we kind of like have a big baby, I would say. So back to this memory mapping issue. So what I ended up coming with, and I think I stole the idea from Tylera. They do pretty much the same thing in the kernel, which was stacking the memory. So we have like those small segments of physical memory, and basically we're going to stack them all together in the direct mapping area, so that we are able to have access to as much memory as possible in our system, and we can really like use the full potential of this NUMA architecture. So obviously, if we have more physical memory than the space that we have in this direct mapping area, we still rely on the high memory infrastructure. So basically what happens is that if we have too much memory, there is this heuristic that is like sort of twofold. The first thing that we do is that we reduce the amount of mapped memory that we want to map per node until we reach a minimum limit. And when we really reach this minimum limit and like everything still doesn't fit, then we start only mapping, we don't map all the nodes. Like we start dividing the number of mapped nodes by 2 and so on until like it fits. And everything that basically is not mapped is, as before, considered as high memory and can be accessed through the K-map infrastructure. To be honest, like, I did not really have time and I did not really have the resources to test that fully, except for really like the boot process. So I was often only able to like boot a platform, a simulation platform, get to the init process, get a shell, and consider that as like functional. I didn't have time to run proper benchmarks, but one thing that we observed even during the boot process is that the memory of the node 0 was extremely overloaded, was almost like saturated because obviously it contains the kernel image, so that's a node that's very used. So one idea that we had and that we tried because it wasn't too difficult was to do some kernel code replication. So basically the idea is that we're going to replicate the kernel image in as many nodes as we can. Obviously, we're not going to like use all the physical memory that we have, but we're going to try to replicate it as many times as possible. And then whenever we run new threads, we're going to patch the page table that they use so that we use one of those multiple copies and hope that it's going to maybe like alleviate the load that is on node 0. And well, actually, not like the increase was only 16% compared to multiprocessor support, so it's quite low. But we were able to boot Linux on a 96 CPU platform with 24 nodes, so that's pretty cool. And well, to conclude, as I was telling you, so this chip SAR is an academic project. There's only one prototype, I think, that's being manufactured at this point. So basically, all that we had was simulation, which is awfully slow. I think it was like at least 24 hours on my laptop to simulate this 24-node system. So yeah, running runtime benchmarks was not possible. One partner of the project had access to an FPGA emulator of the chip, which was still taking like a couple hours to boot and to get to a prompt. So it was still kind of slow, but I didn't have direct access to it. So yeah, unfortunately, like we don't really have runtime results. All that I know, like for the kernel replication, is that actually Linux takes more time to boot with the kernel replication than without, which might be normal because when you do kernel replication, then you have more preparation work to do during the boot, so that might explain. The very good news, though, is that this partner with the fast FPGA emulator, they have an internship starting today, so hopefully we'll have some benchmarks results coming soon. And finally, usually it's the other way around, like you go to ELC and you bribe one of the editors at LWN so they write articles on your talk. But because I don't like bribing people, I just wrote the articles myself about 6 months ago, mostly on just the monoprocessor support. So well, I encourage you to read that if you're interested. And yeah, that's it. Thanks.
So the span of time for this was 7 years, approximately. I mean, based on one of the early slides.
For the.
And I guarantee you, my company would not tolerate that. So what I want to know is, now that you've learned all this and you've published this stuff and I have access to it, how much time is it going to take me if I have to do it?
Okay, I'm still going to address the first part of your question. So the 7 years, or actually the 9 years, was 3 different academic projects. that were very different. My job was a year and a half at the end of all that. And today, if you want to hire me to do this job, that would probably take 6 months, I would say, at most. Even maybe less. I mean, it depends of like the current status of what exists and where do you want to bring it. But if I had to start from scratch on a very new processor, let's say, with my expertise now, yeah, it would be less than 6 months. But once again, like the whole runtime results, I didn't have time to do, and that's also a big part of it. So that would also add to it. And for that, I don't have any number because I don't have the experience.
So can you tell more about the instruction set for the assembly part of this?
So the instruction set for this architecture, when they started this project called SockLib, which was the idea of defining simulation models to prototype systems on chips, they looked at all the processors that existed, and usually a processor comes with its own cache, own model of cache, and own model of virtual memory. And that was a lot to re-implement for all the different families. So they came up with this idea that, okay, we're just going to modelize the ISA of different processors and of different families of processors, and basically the L1 cache and the virtual memory, we're going to define our own, and we're going to make it work with all of those different ISAs. So in what I presented, the prototype is based on a system that uses MIPS32 compatible processor cores, but it could really be anything else. Could be ARM, could be PowerPC, could be like whatever RISC you have on your shelf.
And one of the directories that you had was the headers.
Yes.
And there you specified the architecture.
Yes.
So is that like the 8-bit, 32-bit, 16-bit? What architecture are we talking about?
Can you repeat the question?
Sure. You're asking me which architecture I used in the headers. Well, I used Thor, which is the name of this architecture. Since I started the port from scratch, I called it the name of my architecture, which was Thor.
So the architecture here doesn't have anything to do with the bitness, like whether it's 32-bit, 64-bit?
So in my case, the virtual memory is 32-bit. The physical address space is 40 bits. So basically, you say 64. And the endianness is little endian.
And managing the virtual memory, are you using it like a paging system?
Yes, paging system for the virtual memory. Two-level paging system. The big pages are 2 megabytes, and the small ones are 4 kilobytes.
For some of the parts you talked about introducing a new architecture, like processing with the CPUs and the device tree and looking at stuff. It seems to me like there's a lot of stuff that's essentially just duplicating like boilerplate code into every new architecture. I know I experienced this when adapting Super 8 stuff for the new open hardware J4 stuff and introducing device tree there. It seems like there's a whole lot of stuff where you basically just do the same thing that another architecture is doing, but in a way that doesn't really have any dependence on your architecture. It's just kind of copying the same code. Are there efforts to get this stuff generalized and move to a framework where all architectures can just use the same stuff, things that could be general rather than duplicating it over and over?
Yeah, I think you're right. For definitely, we could keep aggregating for a lot of architectures the way we do things. Often, that's going to be the last question, but.
I can take a question.
Okay, sure, go for it.
So,
No.
So the way we handle it in Linux is basically whenever someone submits a new architecture, I ask them to find all the code that they had to duplicate and make it generic. But it's a long process. Like we've probably come 80% of the way, so we have very little boilerplate code remaining compared to 2 years ago. But there's still some left. And the next time I get a new architecture, I tell them, well, this code looks like that code. Please make it generic.
Thank you.